Final step, now that we have an expression for J, how do we minimize it? How do we find the unknown coefficients such that we get minimal energy? So if you go back to the previous video, we ended up with an expression for J, which was basically a bilinear form. So if you collect all of the unknowns into these columns or row matrices here, then we basically had the following situation. So in the connected numbering scheme, this column vector collects all of the unknowns. So this is a bilinear form. So basically it means that you get all sorts of terms like if you focus, for example, on a certain unknown psi I, you get terms involving the square of that unknown, or also these coupling terms psi I and psi j. So this is the general structure in terms of the unknowns. So how do we minimize this? Well, this is part of the Rayleigh-Ritz procedure, right? So we basically do what's expected. We take the partial derivative of the quantity that we want to minimize with respect to the unknowns. So the unknowns are the psi i's. Again, remember that this is in the connected numbering scheme. We take these partial derivatives and we put them equal to 0. Now, if you look at the structure that we have in terms of the unknowns, after we take the partial derivative with respect to a certain unknown here, it's easy to see because of this square here that we will end up with a linear equation. So that's good news. Linear equations are always fun. So we have a linear equation for each partial derivative that we take, and we take as many partial derivatives as we have unknowns. So at the end of the day, we have a system with a certain number of equations and a certain number of unknowns. So that's good. We can move to your favorite linear algebra package and solve this either directly or in an iterative approach. But at the end of the day, we end up with a set of values for the unknowns psi's, which minimize the total energy of the system. So problem solved. Now, in case you're still a little bit uncomfortable by this physics-oriented approach, saying that we solve Maxwell's equations just by minimizing the energy, then don't be afraid. In a couple of sections, we will also give a formal mathematical proof that this approach of minimizing this energy here is really 100% equivalent to solving the Helmholtz equation directly. So everything makes sense.